Hi, welcome here everybody to day number 2 of CPR. Today's episode is brought to you by the Greek letter theta. And as you can see from the board behind me, today just a continuation of what we did before, just a little bit more on the law of conservation of momentum. And you can see we're going to jump right into a problem. And you can see the problem deals with a 2-stage rocket, and courtesy of Mr. Prok's robotic class here, I have a model of a 3-stage rocket actually. This is the kind of thing that NASA used to get people to the moon in the late 60s, early 70s. And when the rocket was lifting off, of course, the whole thing lifted off. And very shortly, as it burned into the sky, the first stage separated, then the second stage separated, and you were left with the third stage and the capsule. And for the return to Earth, the capsule would would separate from the third stage. Oh, and you'll notice that we had a bit of a technical glitch there. I think the astronauts, they'd be on the radio saying, Houston, we have a problem. But you get the idea. The rocket starts out as one great big mass, and it separates into a whole bunch of little smaller ones. And of course, in the early developmental stages of a rocket, you're not going to start shooting the thing miles up into the sky right away, because it might crash and burn with disastrous results. So instead what they did was, like in this example, they would just run test rockets along a horizontal track. So let's look at our example. It says a 2-stage test rocket moves along a horizontal track at 100 meters per second. An explosion separates the stages, causing the first to move backwards at 5 meters per second. And find A, for starters, the new velocity of the second stage. So standard approach to any problem, get the information that you're given down onto a diagram, and that's what I have here. Okay, here's the 2-stage test rocket with the 2 stages moving together, and the masses, they are given to you. That is part of the given information in the question. So the 2 stages are moving together. There's their masses, 2 times 10 to the 5th kilograms for the first stage, 1 times 10 to the 5th kilograms for the second stage, and of course they're moving together at 100 meters per second. And then an explosion takes place, and it's literally an explosion. There's some kind of a charge between the stages, and it's detonated, and the stages literally blow apart. And after the explosion, you can see the first stage is moving backwards at 5 meters per second. And notice, if this velocity is 100 meters per second to the right, this velocity to the left, it's going to be negative 5 meters per second. And of course, what we want to find out is the new velocity of our second stage here. All right, so let's see if we can solve that. Well, take a look at the diagram. What do you see? I know I see, a bunch of masses, a bunch of velocities. Masses and velocity, they say to me momentum. Whenever you have an explosion taking place, things getting blown apart, or a collision happening, things coming together, okay, think about the law of conservation of momentum. The total momentum of everything before, that'd be the total momentum of all that is equal to the total momentum of everything after. That'd be the total momentum of all that. So let's start solving this. Okay, again, I got an explosion taking place, so the total momentum of everything before is going to be equal to the total momentum of everything after. P total is equal to P total prime. The prime mark there, it of course donates the momentum after the collision or the explosion or whatever catastrophic event is taking place. All right, so what's the total momentum of everything before the explosion? Well, it's going to be the total mass times the velocity. The total mass of everything times the velocity. What's going to be the momentum of everything after the explosion? Well, after the explosion, the momentum is in two separate bits, and we have to add them together. So what's the momentum of the first? Well, it's going to be mass times velocity. And then we got to add on to that the momentum of the second, mass times velocity. And basically right here, the physics is done with. Now it's just a little bit of math. Let's substitute in. Okay, m1, 2 times 10 to the 5th, plus m2, 1 times 10 to the 5th, times the velocity, which is 100, and it's equal to m1 times v1, plus m2 times v2. Now what we have to do is solve, not too hard. 2 times 10 to the 5th plus 1 times 10 to the 5th, well, that's just going to be 3 times 10 to the 5th. What else can we do here to simplify things? Well, how about this? Negative 5 times 2 is negative 10, so this becomes negative 10 times 10 to the 5th. Can't do much with this thing way out on the end. Now what can we do? Okay, well, how about this? 100 times 3 is 300. And I'm going to leave everything else alone for now. Okay. Now look at this. We got a 10 to the 5th in everything. So basically, I'm going to divide both sides through by 10 to the 5th. The 10 to the 5ths are going to disappear. And what I'm left with is 300 is equal to minus 10 times 1 times v2. Or pardon me, plus 1 times v2, which is just v2. You solve this for v2, the 10 goes over to the other side, becomes a positive. And there is your answer. Okay. Doesn't make sense. Well, first of all, it's positive. That's a good thing because you hope V2 after all this happens is going in the positive direction. Also, look at the masses involved. Okay. The mass of everything together is about 3 times more, well, it's exactly 3 times more than the mass of the second stage out here. So this is 3 times heavier than this. That means this should be going 3 times faster than this. And it is approximately. The only reason it isn't going exactly 3 times faster is because this doesn't stop. It's actually moving backwards a little bit. Yeah, and whether you realize it or not, now you know the beauty of a multi-stage rocket. The beauty of a multi-stage rocket is that you get the momentum of this big, massive thing way over here, all concentrated into the momentum of this tiny little piece up here, and as a result, this tiny little piece, okay, it goes like crazy. Okay, let's do part B and part C of this problem now. Now I'm going to remember that this velocity is 310 meters per second. And here's the second thing we want to find. We want to find the impulse exerted on the second stage. Now you'll notice that when I figured this out, I did not talk about impulse or change in momentum at all. I dealt with strictly momentum. The momentum of this is equal to the momentum of this. I recommend you do the same. Okay? But now I got to talk about impulse, because now it's saying, okay, well, what's the impulse exerted on the second stage? Okay? Well, I think everyone's going to agree, okay, that this second stage, it was going along at 100 meters per second, and over here it's going along at 310 meters per second. You know, it obviously had to have some force exerted on it for some time. Remember, that's impulse, force multiplied by time, and there's the impulse. On the second stage, let's see if we can figure that out. What is the impulse exerted on the second stage? Well, I have no idea what the force is. I have no idea how long the force acted for, so I can't just substitute in for these two numbers. But remember that impulse is equal to change in momentum. The impulse acting on stage 2 is going to be equal to the mass of stage 2 times stage 2's change in velocity. The impulse on stage 2 is stage 2's change in momentum. Mass times change in velocity. And now it's just a little bit of algebra, right? Not even algebra, just a little bit of math. Just substitute in. The mass of stage 2, there it is. The change in velocity of stage 2. Well, that's going to be stage 2's final velocity, 310. Take away stage 2's initial velocity, 100. And what does that come out to? 310 take away 100 is 210. So 1 times 10 to the 5th times 210 is the same as 200 times 10 to the 5th. Let's put this in proper scientific notation. I make this smaller by moving the decimal place twice. So that means I got to increase this one by 2. There is your answer. 2.1 times 10 to the 7th. We need some units. We could go kilogram meters per second, or we could go Newton seconds. Doesn't really matter. Seeing as it asks for impulse and not change momentum, I'm going to use units of impulse. Done. Okay. This impulse down here, 2.1 times 10 to the 7th Newton seconds. All right, last little bit here. The very last thing we want to figure out. We want to figure out the impulse exerted on the first stage. This one's a gimme, actually. Think about it for a second. Okay? What exerted this force for a certain length of time on the second stage? Well, what was touching the second stage? The first stage was. The first stage exerted this force for some length of time in the second stage. And of course, if this exerts a force for a certain length of time on this, that means this is going to exert the exact same force for the exact same length of time on this one. So the first stage exerts this impulse on the second stage. The second stage exerts this impulse on the first stage. It's Newton's third law, right? If this one's equal to 2.1 times 10 to the 7th newtons per second, well, this one's going to be the opposite. So the impulse exerted on the first stage is going to be negative 2.1 times 10 to the 7th Newton seconds. Okay. For every action force, there's an equal and opposite reaction force. And you have that assignment called conservation of momentum. You've done a few questions on it. Now everything on that assignment is completely fair game. Just before you take off though, tell you what you can do to make sure that this answer is right is you could say, well, the impulse on the first stage is equal to the change in momentum of the first stage. The mass of the first stage, 2 times 10 to the 5th, multiplied by the change in velocity of the first stage. Its final velocity, take away its initial velocity, which is 100. You do this arithmetic. Negative 5 take away 100 is negative 105. Negative 105 times 2 is, negative 210 times 10 to the 5th. That looks familiar. That works out to 2.1 times 10 to the 7th Newton seconds. Okay. So there's a quick little check of your work. All right, as I said, you can work on the rest of that conservation of momentum assignment, which you have already. Tomorrow I will post a video going over any questions that you don't have answers to, and we'll also take a look at the next topic, which is the vector nature of momentum. Bye for now. Enjoy the rest of your day. Don't forget to wash your hands.